Hi guys, we are for right now because of the sheer complexity and total annoyance of 3.6, we are going to have to forego that section. It is very, very intense, and without actually being there to coach you and be like right there with you as you're working through these is because I'm not there. It's just almost an impossibility. So 3.6 is something that, and it's not on your test either. There's nothing on there that has you drawing a graph. But the concepts involved, finding the max and the min and the concave up and concave down, okay, that is still valid. Okay, so you do need to work on 3.1 through 3.5, and now we're on 3.7. Optimization problems. Okay, so the idea with optimization problems is that you will have two equations. One of those equations will be your main equation. That's the one that you're going to be finding the derivative of to either maximize or minimize that function. Remember, a function is at its max or its min when its derivative is set equal to 0. Okay, so that will be one equation that you have. The other equation that you will have in an optimization problem is going to be the equation that you use to either solve for X or Y and make a substitution. For example, looking at example 1, we're on page 211. We're looking at finding a maximum volume, okay? A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So our maximum volume, first of all, we're just going to look at the box here. It's kind of wacky, but whatever. Okay. So the bottom has dimensions of X, and there's the height, okay? So the volume, the one that we are maximizing for this particular drawing, volume is length times width times height, okay? Length is X, width is X, and height is H. So our volume equation is X squared H. Easy enough. The other formula that we need is for the surface area of that box. So remember, surface area is the area of the base plus the area of each of the four sides. So the area of the base is your X squared, because the base is a square and area is X times X. And then we have four sides that each have an area of X times H. Okay, now we need to use this equation right here to solve it for one of those variables in order to plug back in over here. Okay, so we only have, remember, we're solving for the dimensions that will produce this box with maximum volume. That means that we need to be able to either solve for X or H, okay? So the equation for the surface area, okay? Well, we can either solve for X or we can solve for H. If you look at possibly trying to solve for X, that's not going to work. You cannot solve that equation for X. Therefore, we have to solve it for h. Now, the surface area that we are given is 108. So, 108 equals x squared plus 4xh, and 108 minus x squared all divided by 4x is equal to h. Now we can use that to rewrite our volume equation. X squared times what h is equal to. Okay, so I'm going to do some simplifying. I'm going to get rid of that x and one of those. Okay, then we end up with the volume is 108x over 4 minus x cubed over 4. So that is what we need to find the derivative of. Okay, so I'm losing my... Okay, I'm just trying to decide what I can erase. I'm going to erase that in my beautiful drawing. The only thing we'll need after this is what h is equal to. So I'm going to start back up in the upper left. So here is our volume equation in terms of x only. So in order to simplify this, because it really doesn't need to be that complicated looking, remember 108x over 4 is equal to 108 over 4 times x, and x cubed over 4 is the same thing as 1/4 x cubed. Now taking the derivative is really simple, because the derivative of 108 over 4 times x is just 108 over 4, and the derivative of 1/4 x cubed is going to be 3/4 x squared. So now that the denominator is the same, our derivative is 108 minus 3x squared over 4. Now to maximize that, we need to set that derivative equal to 0 and solve for x. And when we solve for x, that is giving us the x dimensions of the base of that box. So 108 minus 3x squared is equal to 0, and 108 is equal to 3x squared. 108 divided by 3 is 36. And now normally when you take the square root of 36, you would allow for the negative, but we know that we cannot have a side length of that box that's negative. So now we solved for what the base length of the box is, and we can plug 6 in to the h equation and solve for the height. So 108 minus 36 all over 24. So 108 minus 36 divided by 24 gives us that the height is 3. Okay, so those measurements will produce the box with a maximum volume. Okay, now that's helpful when you only have a specific amount of material available to you. You want to be able to maximize the amount of the volume while you're minimizing the amount of materials you're using. Okay, think business, maximizing your profits. The less you spend to create your product, the bigger your profit is. Okay. All right, example 2. So we're going to do a couple of the examples, and then after that, what we're going to do is a couple of the homework problems, just so you have an idea of what you're doing with them. Okay, so for example 2, you're minimizing a distance. So which points on the graph of y equals 4 minus x squared are closest to the point 0, 2? So if you look at the drawing, 4 minus x squared is an upside down parabola with the vertex at 0, 4, and the point 0, 2 is the y-intercept. Okay, so those dotted red lines are going to be the just an example of the shortest distance that they're looking for. So when you're looking for distance on an XY coordinate plane, you are also using the distance formula, okay? And if you're minimizing the distance, then this is the formula that you're going to find the derivative of, set it equal to 0, and solve for one of your variables. Okay, so D equals x minus the x coordinate of 0 plus y minus 2. Now, for right now, we still have 2 unknowns in that distance formula. We're going to change that by taking what y is equal to what y was given as 4 minus x squared and putting it in for y in our distance formula. And notice it says because the distance is smallest, I'm reading from the book, under example 2, because D, distance, is smallest, when the expression inside the radical is smallest, you need only find the critical numbers of what's under the radical. So we can drop the square root. Now y is 4 minus x squared minus 2 squared. Okay, so x squared plus 2 minus x squared squared. 4 minus 2 is 2. So we do need to distribute. So x squared, if we multiply that by itself, we're going to get a 4 minus 4x squared plus x to the 4th. I did that in my head. I hope that's right. And then let's combine like terms and then I'll check it. So x to the 4th minus 3x squared plus 4. Okay, now that is what we're finding the derivative of, because remember, that is what we are minimizing. Okay, so let's just call that d prime. It's 4x cubed minus 6x. Now we'll set that equal to 0 to find those critical numbers. In other words, to find that point where we've got either a max or a min. So we can factor out a 2x And we're left with 2x squared minus 3. So 2x will equal 0 and x equals 0, or 2x squared is equal to 3 and x is equal plus or minus the square root of 3 over 2. So those are the critical numbers. Now, what we need to do with this particular problem is set up our interval table. Okay, so from negative infinity to the lowest critical number, and then from that critical number to 0, from 0 to the next, and then we'll take that, yikes, whoops, it's a mess, but I'm just going to leave it. Okay, and then test numbers. -2 is in that region, -1, 1, and 2. So what you'll do is you'll throw those test numbers into the derivative, which is a very, very simple polynomial. And here you'll get a negative, a positive, a negative, and a positive. Okay, so we're looking for the minimum distance. Well, if we're changing from negative to positive, from decreasing to increasing, that is where we have a min. If we're going from increasing to decreasing, that's where we'll have a max. Well, we're not looking for a max. And then from the next region to the last region, we are decreasing to increasing, and there we have another min. So those two x values will give us the y values that represent the min, or the minimum distance. So when you plug those in, you get 5 over 2. You plug those into the original, and you get 5 over 2. Okay? So that would be the points on the graph that are closest to 0, 2. Okay? All right, so for the next and final example, we're doing area of paper. Okay, this is a very cool problem. It says a rectangular page is to contain 24 square inches of print. So we have a rectangle as our shape. Square inches mean area. So we have an area in terms of x and y as our one formula, and the area is 24. The margins at the top and bottom of the page are to be 1.5 inches. So 1.5 and 1.5 is 3 inches altogether, and the margins on the left and the right are 1 inch each. So that's 2 inches. So what should the dimensions of the page be so that the least amount of paper is used? Okay, so once we add, so I don't know where I can do this drawing over here, I guess. There's the writing, very not to scale. All right, this is 1.5 inches. Oh my gosh, that is not writing. 1.5. This is 1.5. This is 1, and this is 1. Okay, So if this is x and this is y, x is now x plus 1.5 plus 1.5, which is x plus 3. And y going across goes all the way, so it's y plus 1, which is y plus 2. That's the area now with the writing and the margins. Okay, so we have 24 equals x plus y, and because we are minimizing the amount of paper, this is the equation that we are going to be using to find the derivative. Therefore, the other equation is the one that we're filling in as our substitution. Okay? So you could either solve for x or y. It's more common just to solve for x. So we have y equals 24 over x, which means that over here, our area formula is going to be x plus 3 times y, which is 24 over x, plus 2. Now, we could use the product rule, I guess, and find the derivative of that. Okay, so x plus 3 times the derivative of 24 over x, because the derivative of 2 is 0, we would get x times the derivative of 24 minus 24 times the derivative of x all over x squared. And of course, again, the derivative of 2 is 0. And then, that's only half of it, we have plus the 24 over x plus 2 times the derivative of x plus 3, which is just 1. Okay, so we have a prime is equal to x plus 3 times negative 24 over x squared plus 24 over x plus 2. This is just all your algebra now. So we're going to distribute negative 24x over x squared minus 72 over x squared plus 24 over x plus 2. So negative 24 over x minus 72 over x squared plus 24 over x plus 2. And your negative 24 over x, your positive 24 over x, gives you that a prime is equal to negative 72 over x squared plus 2. Now we'll set that equal to 0 and solve for the critical numbers. So 0 is equal to negative 72 over x squared plus 2. And then if we move over the 2 and make it negative, if both sides are negative, both sides are positive. We'll solve that for x squared. 72 divided by 2 is 36. So x equals 6. Okay? So if x is equal to 6, we're going to come back up to the y equation and say y is equal to 24 divided by 6. So y is equal to 4. Okay? So the dimensions of the page would be x plus 3 up here, x plus 3, and x is 6. So the dimensions of the page would be a length of 9 and a width of 6. X is 6, and 6 plus 3 is 9. Y is 4, and 4 plus 2 is 6. So those are the dimensions. What dimensions of the page? What dimensions, oh my gosh, what should the dimensions of the page be? So the least amount of paper is used. Okay. Now, those are your examples. Remember, again, you will need 2 equations. One is going to be the one that is used sheerly for substitution. The other one is going to be the one that you are taking the derivative of to either maximize or minimize. Okay, so I'm on page 216, and it says in exercises 2 through 6, find 2 positive numbers that satisfy the given requirements. Okay, so we'll do number 2. It says the sum is S and the product is a maximum. All right, so the sum, x plus y, is equal to the sum, and the product is a maximum. So the product, okay? So the product is what we are taking the derivative of because we are maximizing that, okay? So we can go back to the sum. Okay, this probably wasn't the best example, but only because it's a little more awkward than the others. Anyway, it says the sum is S and the product is a maximum. Okay, this one really doesn't have any numbers in it, which is why it's a little bit more difficult to follow, but we'll do this one and then we'll also work on number 4. In fact, you know what? Let's just work on number 4 and forget that one. All right, number 4. The product is 192. So x times y. Here we have some real numbers. So understanding this with numbers is much, much simpler than in the abstract. And then the sum of the first, so the sum of the first plus 3 times the second is a minimum. So 3 times the second is the sum. And we are minimizing the sum. Okay, so we're going to go back to our other equation here and solve it for y. And then we can plug that in for y. Simplify. So again, this is nothing but algebra here. X plus 192 times 3, 576 over S, or X equals the sum. Okay. Now s prime, the derivative of x is 1, and then we'll have to use the quotient rule. So x times the derivative of 576 minus 576 times the derivative of x all over x squared gives us that the derivative of the sum is 1 minus 576 over x squared. Okay? Then we're going to subtract the 1, and if both sides are negative, both sides are positive. Solve for x squared. X squared is equal to 576, and the square root of 576 is 24. Okay. So we know that one of the numbers is 24, and when we plug in what x is equal to, we can solve for y. So 192 divided by 24 gives us that y is 8. So those are the two numbers that when you have a product of 192, the sum of the first plus 3 times the second is a minimum, and then that gives you what those numbers are. Okay? Other than that, you should be fine. So I'm going to write your homework here, and then I will also put it in chalk. I'm just looking at my book and writing down what I have circled. 17 and 18. 22, 23. Oh, you guys are going to love that one. And that should do it. Enough is enough, right? Okay. All right. There you go. See you guys.